Hello, everybody. Welcome to today's session of nTop Live. My name is Blake Corder. I'm the Chief Technology Officer here at nTopology. And today I wanted to show you some what I would call intermediate modeling techniques. You see a lot of cool stuff, and it's pretty easy to make lattices and do topology optimization and a lot of the things you see commonly done with our software. But there's a whole nother world of modeling that's available to you. And I thought I'd take a few minutes to give you all a little sense of what that feels like. So let's start with a few basic shapes and just remind ourselves that we're working with distance fields and what those are for just a second. So what is a distance field? Distance field is it's a way of representing a shape using more information. So let's just take a look at this sphere for a second. I've turned on some tools to view the field. We can look at the values. It's 0 at the surface itself. And then as we go away from the model, our distance field gets bigger. As we go inside the model, it goes negative. Let's take a look at the inside geometry here. So we have negative values and positive values. And that's what a sphere looks like. It's actually the simplest thing you can do in a distance field. We also have our cube over here. Let's look at that field. This one's a little more interesting. It's got it's got straight and rounded features on the outside. On the inside, it's got these sharp features that are called medial axes. Those will come up again later. It'd be nice to be able to see our sphere and the cube at the same time. And one thing to observe is that since our parts are the lowest values, if we want to see them both, we just have to ask to see the lowest values of both. Now, in nTop, there's a Boolean union operation that normal people would use to do this today because we're doing things intermediate. I'd say that the main quality of doing intermediate level modeling in nTop versus basic modeling is that you stay aware of your fields. You're not just focusing on where your surfaces are, but you're just staying at least loosely aware that you're working with these field contexts. And so in that way, you get comfortable with the idea of working with min and max, just like you would a union or an intersect. You don't need to do that to get started, but you'll find that it's all part of the same thing. So we min these together, and now we've got the low parts here and the low parts there. There are both of our shapes, and you may notice that right here in the middle, right in the very middle, we have this thing called a medial axis showing up again. And when you're looking at fields and you see these even offsets and these sharp features, usually that's a pretty good sign you're looking at a distance field, at least in your region of interest. Okay, so that was pretty cool. We did a basic math operation. Let's take a look at some other math operations that might not immediately be as intuitive. So one nice thing to do when working in nTop is to make a few variables here. We'll be using these over and over again. When I do this kind of work, I like to call them A and B. So I'll be repeating myself. We're talking about A and B a lot. All right, well, what do you do with numbers? Remember, these fields are just numbers, scalar numbers. Let's add them. I think that's the first thing you do when you come across numbers, right? So drag them in here, and let's look at our A plus B field. Okay, there are no negative values. Maybe it would help for reference to see our shapes. And if looking at the values inside the field, we can see pretty much everything in between them is around 10. What's up with that? Well, just to get the context, this cube is, these guys are centered 20 apart, and they're both of basically size 10 side to side, meaning there's exactly 10 millimeters of clearance between them. And somehow by adding these fields together, we've measured that. That's surprising. At least it surprises me to this day. And if we just move the sphere over, let's, wrong guy, move the sphere over. And make them interfere with each other a little bit. These guys are overlapping. But where they overlap, we now have negative values. And we have a local measure of interference everywhere. This is astonishing. And if you're thinking, does that seem useful? It is. For example, if you were trying to make a scale model of an assembly and you wanted to have all the parts like just have nice little slide fits like to put on a desktop, you can easily remove all the interferences from your model and make something that prints at a different scale. Or if you want to force a press fit, all these things, you have complete control over clearance and interference when you're dealing with implicits. That's just a little aside. Okay. Okay, we added fields. What's the next thing you do with numbers? You subtract them. Okay, we'll subtract A and B. It doesn't really matter what order. Let's take a look at what we got. Whoa, that's pretty. Huh, what are the values in here? Well, now we're getting a lot of, the lines mean across the lines, the values are changing. Along the lines, the values are the same. And so we're going from like -10 to +10. That was our clearance. Yeah, we're going from negative clearance to positive clearance when we subtract them. And also, this is kind of cool, right in the middle, right where those medial axes, where we get this beautiful mid-surface field. And if you've ever like needed to like extract a midplane from some complicated CAD geometry and it was saying there's no good way to do it, this is a good way to do it. It always works. And we'll be taking advantage of that later in the demo. All right, so we've got an A plus B, that's the clearance. We got an A minus B that ranges the clearance. What happens if we divide? All right, so we're gonna divide A minus B by A plus B, because that was sort of the denominator. Now let's see what we get. Our lines went away. We did rescale things. Let's just crunch it up and see, whoa, what do we have here? So now we have a field that's still ranging between them. It's -1 on one side and +1 on the other side. If you've been using nTop for a while, you should say, wait a minute, that's kind of like a gyroid or a TPMS, The idea of ranging from -1 to 1 is a very useful non-dimensional way to work. And will we, by and some of you, when I say the word non-dimensional, it might remind you of fluid dynamics and some engineering activities. It is very much the case that working with non-dimensional numbers reduces cognitive load and makes things more intuitive. It is a little bit more work to sort of get to non-dimensional land and get back out of it, just like it was in engineering problem sets. But when you do, you become more powerful because you can apply the same concepts to very different situations. And so we've just gone non-dimensional here. We will be redimensionalizing as we use this field. But also, of course, you'll notice our surfaces are interpolating perfectly from one body all the way around to the other body, going through these infinite planes in the middle. This is truly astonishing. And I don't know, I stumbled across this one day. If anyone knows other people that are doing this kind of work, I'd love it if you'd introduce me to them. And mainly, this is sort of the opening gambit of a lot of modeling operations in nTop, especially when you're starting with CAD geometry. And so, to me, this is sort of one of the most important basic moves of implicit modeling that is also, I think, one of the world's best kept secrets. I apologize if that's partially my fault. So what are we going to do with this? This theme's useful. Let's keep it. The first thing I want to do is we've defined it to work on a cube and a sphere. Let's make it work on any old scalar field, and we'll make those inputs to our function. Everything in nTop is a function. And then this is what we'll output. And I like to call this thing a two-body field. If there's a real name for it, please tell me. You know, we think we could spell. And we'll save it. Sorry, that's off your screen. Okay. What else could we do with this? If you tuned into Gabby's webinar on Friday, Gabrielle's webinar on Friday, she was showing a lot of remapping techniques. And before we do anything else, let's just sort of connect from her excellent presentation on Friday to this kind of trick. So she was remapping gyroids. So let's remap a gyroid. And I'll use the field version of the gyroid because it's non-dimensional, and that's kind of within the spirit of things. I also find it easier. We can give it some reasonable period. So here's our gyroid field. We don't need the contours anymore. And we want to remap it to space. We'll just do it in the x dimension. So we'll leave the y and the z values the same. For the x dimension, we're going to use our two-body field. Normally, I would make more variables for this, but just to get things done, I dragged it in. We have an error. And that's because, like I said, we're working with non-dimensional numbers here. So to deal with that, we'll add the dimensions, and we just need to multiply by a unit of characteristic length. And it's like when you're learning about Reynolds number, what does characteristic length even mean? How do I know what length to choose? It is a bit of a fudge factor, frankly. And when you're doing engineering analyses, you just need to pick a common one. But this doesn't look really right. And although we give you a lot of help fixing unit issues, these conversion factors are really important constants, often meaningful experimentally. We could try using the separation here. Notice it's a constant value, not a field. So you have got you're fitting a scalar to a field when you're doing something like this, which is going to be error prone. I happen to have done this before. I know that we're going from -1 to 1 in our field. And so that means that over a range of 1, we actually want to have half the interval. Usually you'd have a little computation for this. But the point is that in the neighborhood of interest here, which let's say is between our two shapes, we've created a really nice parameterization. Outside, it may be a bit squirrely, but you're allowed to do that. You only have to make things nice where you need them to be nice. And then over here on the interface with the sphere, you can see that the same part of the gyroid is kind of sucked on everywhere. We've matched that. Some people use the word conformally to describe what's happened here. Other people think that's a more nuanced math term. But regardless, we've gotten our interface lined up right with the sphere like that. And this is incredibly useful if you're doing something like making a heat exchanger and you want to have a bunch of nozzles along there. Let's just take a look at what that would look like. We just need to add to our field a little bit to turn these into nozzles. So we'll do another, this is arithmetic add operation. We'll throw our field in there, and to that, we will add a bit of ramp. And we will ramp from our sphere. And we want to go from just a little bit inside of it, like -0.5 millimeter to 1 millimeter. And over that, we're going to go, remember we're working non-dimensionally, so we don't have to worry about size. We just know that it's going to be fully offset on the inside and not offset, sorry, on the inside of the sphere and the outside of the sphere, we don't want it offset. And that's everything we need to know to take a look at this thing. And you can see we've created this gorgeous sort of field of nozzles, and they all have the same kind of leading edge. We've gone skew because our axes are no longer of remap, are no longer perpendicular here, but you can see every little one of these nozzles is dressing the body in the same way. And if we are engineering a heat exchanger and we actually have some parameters over how we want to change the pressure in our convergent nozzle here, you have that control. And you can say, actually, let's give the fluid a little bit more space to compact. And you're really engineering an interface that is also something that has controllable fluid properties. So that's pretty neat. And just to see this applied, about a year ago, a customer gave us a cool example. This is a completely remodeled version of it that sort of shows through the same spirit, where we've taken a CAD part that has some kind of complicated interfaces on it. Like these guys. So this is a really, again, actually, these could be overlapping and a lot nastier, frankly. But we can take this as one of the sides of our two-body field, as well as another face over there. And you can see we create this gorgeous parameterization. And then around the thing, instead of using a two-body field, we're actually using cylindrical coordinates. And you can actually create these different fields using a combination of distance fields and these two-body fields and other convenient fields to create all these amazing different remappings. And then you get these gorgeous flow lines. These are not streamlines, these are distance field lines, but quite useful, also useful for other kinds of manufacturing processes. And then to take a look at this with the actual TPMS on there, just right here, you can see, it's easier to see on the other side. Got all these little sharp edges in there, but it's all perfectly aligned and the same and warped, and you're just in control of your work when you do things this way. Let's look at those gyroids just for a sec. So that's how that goes. All right, so now let's do something useful with all this technology. We did save out that field for later. Let's take advantage of it. I don't see any, at this point, I might take a breath and answer a question, but there are no questions yet. Feel free to type them into the chat here as we go. All right. So let's bring in our two-body field that we saved before. And I did leave all those inputs in there, so it'll give us something to look at right away. Now what I wanted to show you how to do is make some ribs that use one of these fields, kind of like you saw in that last part. It was made with a bunch of intersecting ribs. Let's cover how to do that. I'm going to bring in another friend here, the what I call a triangle wave. And when you hear the term triangle wave, you think synthesizers. You're right on the spot. Any knowledge you have about doing audio processing and working with synthesizers applies to this. It's just 3D instead of 1D. And yeah, it's all true. We don't have Fourier transforms yet, but everything else, they'll probably come in sometime too. It all works, and it's quite amazing. What I'm gonna do is drag this guy in here, and we'll give it some period. I'll actually use the same period we've been using for the contour intervals. So if we switch back and forth, I've just made this is a cosmetic feature. It draws lines and contours so you can figure out what the heck you're doing. I've just turned that into a geometry feature by throwing it in a triangle wave. I guess you can see we're just zigzagging. We're just folding our field back and forth on it to make a bunch of little bands. And the reason we're doing that is we're going to thicken them. Again, you could use a thicken operation or an offset operation. Again, because this is a video about sort of intermediate level modeling, I'm going to do things with the lower level values and just offset a little bit. Now, this is actually being offset. This is still our non-dimensional field. And if I try to offset it by a useful value like 0.1 millimeters, it's going to throw me an error again, because units are good. They keep you doing reasonable things. And again, we use this sort of this match units capability, and we know it's around 5 is a reasonable value, and we can make some ribs. So now when we subtract them, we get these little ribs. Let's make a few fewer ribs, something like that. And this is cool. We've made the ribs are the pink parts. You probably want to see a solid by now. Let's make a solid so you can see what it looks like in 3D for those of us who are into the 3D. Something like that. What are we gonna do? We're gonna intersect our block with our new sheep. And there you go. Let's move the field out of the way for a second. So that's kind of cool. Got a lot of ribs in there, but you know, when I see ribs, I usually want them to be constant wall thickness. And these are not that. So how you know, this is very pretty, but it doesn't seem very useful unless we can make our ribs constant wall thickness. How are we going to do that? Well, it comes back to this triangle wave and this fudge factor. By the way, I don't like fudge factors. It usually means either you need to do experiments or you don't know what you're doing. So let's fix this. I'm going to make this guy a variable because this is the field of interest, and show you something called a gradient. This is a derivative in space. Don't freak out if it sounds like we're getting into calculus. Calculus is just a tool that explains very intuitive concepts in a complicated way. But we're going to call this guy a gradient, and we're going to drag the scalar field in. And what this makes is a kind of, well, it's a vector field. Let's just for fun look at a component of it. And we'll look at the x component over here. And it's just another field with different properties. And what we're actually interested in is the length of this field, which isn't very interesting to look at there, but hang on a sec. What we're going to do is, instead of multiplying our field here by some fudge factor, I'm going to divide. And we're going to divide our field, which is dimensionless, but it actually doesn't matter what units in, because when you take the derivative of something, you get the units divided, well, when you take the derivative with respect to length, you're dividing by length. And so when you divide by your thing by dividing by length, you always end up with units of length. And you don't need any fudge factors because you have a distance field. And you can see everything is nice and happy. Get these contours off. Okay, those all look constant everywhere. What about our solid here in the background? And everybody here is nice and constant walled too. It's amazing. So just by dividing, if the field isn't right. Oh, one other thing we should see. Let's look at some contours here. Look at that. We've constructed these medial axes. So these didn't exist before. There were no such medial axes. It was all stretchy. And yet somehow when we come over to this one, we get nice, perfect medial axes. It's amazing, right? And we get perfect wall thickness fields. All right, this also seems useful. We've just invented how to do constant wall thickness fields, just creating a series of ribs between two bodies. And again, this is what happened. This is pretty much what happened in that previous result. So let's make use of this downstream. We want to make one more little block here called, we'll call it something like ribs. And what do we want it to take? We want it to take the thickness value here. This is technically the half thickness, but we should divide, but in the interest of time, we'll just call it thick or think, whatever the heck we called it. And then over here, we have the period, which is 0.2. That doesn't seem very useful. That's a non-dimensional user. If I were going to see this, I don't know what that means. Let's make that a little bit more useful. And what we'll do is, I'm just going to divide 2 by some number. Why 2? When we're playing with non-dimensional numbers, sometimes they work from -1 to 1, sometimes they work from 0 to 1. But the important part is that you got to deal with that, and so that 2 deals with that. That wasn't a great explanation, but sometimes, yeah, sometimes you're going to be off by a factor or 2 or by a negative sign, and that's totally okay. I prefer to visualize things and measure to make sure I'm doing right. If you overthink it, at least, well, I get it wrong in my head half the time anyhow. And then finally, what's the last thing that we want to put as the input to this block for ribs? We could give it 2 fields and make it a 2-body rib kind of job. In this case, I think it's just a little bit easier to give it a field whose range we know. So that's this one right here. We'll make that a variable, drag it on up here. And we'll have it range from -1 to 1. This is just an annotation. I do this because sometimes I like the fields to go from -1 and sometimes from 0 to 1. So we'll just document that here. So we've named our function. We need to make sure our function has its output. And in this case, we want to output the offset field here. A few more variables and comments would make this more reusable, but we're given a demo. So we'll call this guy ribs. And now let's put it to work. So I have one more design brought up here. And this is something I brought in from a CAD system. I think when you're using CAD, you should never use your own geometry when you're starting, because most of our customers aren't doing that either. And you really got a real world geometry is quite different from the thing that you whip up real quick in CAD to get a demo done. In this case, credit where credit's due. This is from Yerker Jung, posted to GrabCAD. And you can see all these little surface patches and stuff where, well, those are one of the funny things B reps do, and they're baked in here. So that's the part I downloaded. You can see we brought in the whole assembly here, which we don't really need. I've used the splitting of the surfaces to create basically 2 halves of this tube. Now, if you're already in CAD and doing stuff, there might be a more kind of reasonable way to do this. And I should also point out this example I'm showing you is a bit of an extreme example to demonstrate the power of these tools. I might not make this actual design this way, but let's have some fun. So this is the U field we've already set up between these two surfaces. Similarly, here's the V field. And the challenge today, to back up, is let's say you wanted to create some flow guides in this to reduce turbulence. Basically, we're just going to fill this thing with a rib structure that goes parallel through the tube to let you keep the flow moving nicely, or maybe it makes the thing stiffer. Obviously, this would have to be additively manufactured or something expensive. So now let's put some ribs in here that create that field. First thing I'll do is let's import the block we just made. So we called it ribs. We'll bring in ribs. There it is, typo and everything. And as the field for our ribs, let's start with the U field. Don't really need to look at it, but we'll look at it in the field viewer. Turn off the contours. And we can increase the thickness here a bit. And so here we've created this field between these two quadrants of the tube. And similarly, make another one. Here, I'll make a variable for this guy. Share the, oh, look at the spelling propagates. Bring this one in so we can take a look. Let me see here. So here we've got these guys and they're based off of U and V, and that seems pretty reasonable. Now, as you're looking at this, you might be like, okay, that's kind of a neat trick, but it's a little lumpy and stupid. And by the way, if I were to split this thing into fourths, I think I'd want to see my lines at 45 degrees from here, kind of going up and down, not diagonal. And look, the reason for the little bumpins in there is because the section plane isn't even parallel. I mean, the ridiculousness of the geometry is intentional. But I'm going to show you how to fix this. And I thought it'd be fun to come full circle. We started the demo by looking at basic arithmetic operations on fields like a plus b and a minus b. Let's do that again. And so actually first we'll union these together. And here I'll use a proper union as a distance field because you never know when you're going to want to put a round or a chamfer on something. And this has all that built in and it works beautifully. So here we can see the pair of these. And it's cool, we've got some compartments, but they're different sizes and stuff, right? It doesn't seem right. So we'll make a copy of this guy. And instead of using the U and V fields, we'll put an add in here. And we'll put a subtract in here. And into them will go U and V. And we'll put the field viewer on it. And now you can see we've created this gorgeous square grid. It's a little twisted, our plane's a little warped, and it's not perfectly square. I mean, it seems kind of absurd to me to even believe that out of this crazy twisted tube, one would get this field. Let's just look at these back and forth again so you can get a feel for it. There's so this is the U and the V field, and these are, when you add and subtract them like this, I like to call these the UV and the VU fields. But this creates a lovely result, and had we actually tried to prepare the geometry in a reasonable way, you can see this would be much more powerful, especially if we had some curves and stuff in CAD to use to build those surfaces. So at this point in time, I'll turn it over to questions. This is pretty much what I wanted to show you. The main points were that there's a lot more power in nTop if you're willing to go a little bit closer and look at the fields and look at their remote values. That in particular, adding and subtracting the fields gets useful very quickly, and the A minus B over A plus field, AKA the two body field, is the opening gambit to almost every useful modeling operation in field synthesis and field design that I've come across. And that when you use these tools on imported CAD geometry, you can do absolutely amazing things with very little work up front in CAD. And I think it helps illustrate how CAD and nTop can work very closely together to create consistent, robust surfaces in geometry in situations that you never otherwise would have imagined. So here, let me turn this thing on and get it crunching for everybody. And it'll take a minute or two to compute the whole body, but hopefully by the time we're done answering questions, something will have popped up on the screen. Let's see what we got. Okay. Triangle wave is a custom block. Is it available on any of the toolkits? It's not yet. It should be. Let's take a look at that. I encourage you to make your own. It's and we can certainly share these and post them with some follow-up. I think in general we could do a lot more there. Let's take a look at this in the X direction for like a 1 millimeter period. So this is the triangle wave. Something you'll see a lot of folks do, I do it myself, well, I did it before I had this block a lot, is use a sine wave to do basically the same thing, or a cosine. And that's fine, but you end up, if you want the period to be exact, you end up, you gotta put some pi in there, and then you gotta figure out what to do with the output. And if you offset it, it's not linear, and you don't have a true distance field. So you can see, in fact, I think if you go to the Wikipedia page for triangle wave, it gives you basically this equation. But it's a good excuse to get comfortable with modulo and divide. And, you know, I have a feeling that a lot of the folks watching this are engineers, and a lot of engineers are also good at craft and have skills. And, you know, like if you're a woodworker, sometimes you gotta sharpen a blade. And I think most woodworkers prefer to sharpen their own blades than have someone else sharpen their blades for them. Sometimes. It really depends. And this is one of those cases where I feel like you can do a little bit a better job if you sharpen your own blades sometimes. But absolutely, this type of thing needs to be in a toolkit. And there's a lot of ongoing work to take these kind of capabilities and make them easier to use. So when I'm out here showing you things of, you know, from more advanced modeling practices, please understand there's a whole team of people at nTopology that are making new blocks and new toolkits to try to take some of these techniques and technologies and make them push button simple for the folks that don't feel like learning about the math of vector fields just to put some cool ribs into a tube. Okay, returning back after Q&A, I realized that I had forgotten one step, which took a little longer. So I went ahead and re-rendered this for everyone so you can see the final part. You can see that we have that profile we wanted all the way through. It goes through the entire model with the same geometry and results, regardless of all that crazy noise that was in the original model. You can see it just perfectly matches up with our original surface geometry. So again, this may not be the ideal way to make these tubes, but it's pretty amazing that you can just get it done this way and work with such crazy imported data to produce such fluid results. I'm going to call it here and end for today, but thank you all very much for attending. Take care.